Let's jump right into this. Welcome, focused learners, to today's explainer. We are diving deep into conquering the Cambridge Computer Science exams. Whether you're sitting for syllabuses 0417, 0478, 2210, or 9618, this session is your ultimate strategy guide. We're zeroing in on a notoriously tricky topic, the reasoning behind image resolution and color depth. Now, if you've ever felt like you've literally memorized the entire textbook but somehow still lost marks on the actual exam paper, you are in the right place. To show you what I mean, I want you to imagine two students. Let's call them Alex and Sam. They are both taking their computer science exam, staring down a 4-mark question. Alex is our classic over-preparer. Alex overloads their answer with raw computer science facts, just dumping every single definition onto the page, but completely missing the analysis. Then we have Sam. Sam rushes. Sam completely misses the command word requirements and writes a vague, generalized answer that doesn't actually solve the problem. In this explainer, we are going to look at their flawed answers, see the examiner's red pen marks, and completely transform how you approach these concepts. We're moving away from isolated facts and straight into the strategic reasoning that examiners are actively searching for.
So, let's look at the actual challenge. Here is a realistic digital scenario, straight out of a past paper style question. You probably know the definition of color depth, right? It's the number of bits used to represent the color of a single pixel. But can you explain why an automated robot's camera on a fast-moving factory assembly line needs a specific resolution? Here is what Alex wrote. Image resolution is the number of pixels in a given area. High resolution means more pixels. Color depth is the number of bits per pixel. This means the file size is larger. The examiner's score? 2 out of 4. Why? Because it's just rote facts with no link to the factory robot. Now here is Sam's rushed answer. High resolution makes the picture clearer so the robot can see the defects better, but it's too slow. Score? 1 out of 4. It's incredibly vague. What does too slow even mean in computer science terms? Posing this realistic scenario instantly bridges the gap between knowing an isolated fact and applying it to a practical problem. Understanding the theory is only step 1. Knowing what digital problem that theory solves in the real world is what actually gets you the marks.
To get you scoring full marks, here is our roadmap for today's explainer. First, we'll unpack the rote learning trap. Second, we'll learn about thinking like an examiner. Third, we'll cover the 3 pass revision method. Fourth, we'll introduce the 4 prompts to success. And finally, we will build your ultimate pre-exam checklist. By the end of this, you won't just be answering questions, you'll be engineering responses.
Let's kick things off with Section 1, the rote learning trap. This is where we dissect the fatal flaw that caught Alex out and show you how to actively avoid it.
Memorizing definitions is a really weak approach. In Cambridge computer science exams, you simply do not reach the highest grade boundaries by writing short labels or reciting isolated facts alone. Contextual understanding, however, is your superpower. You have to understand what digital problem the resolution or color depth is actually solving for a specific system. To do this, top students use a framework called PEAL. That stands for Point, Evidence, Explanation, Link. Instead of just stating a fact, you make your point, provide technical evidence, give a clear explanation of the process, and then link it directly back to the scenario. If Alex had used the PEAL framework, their answer about the robot would have linked the larger file size of a high-resolution image to the specific problem of the robot's microprocessor taking too long to analyze each frame, causing it to miss defective parts on the conveyor belt. That is contextual understanding.
To build that contextual understanding, we must avoid some classic wrong turns. Sam fell right into the vague wording trap with phrases like, makes the picture clearer. You also lose marks by confusing similar terms or missing crucial process steps in your explanation. A massive trap is naming a device or a method, like simply writing, use a lower image resolution, without explaining how it actually works. And finally, never give an advantage without a reason. When you write down an advantage of a higher color depth, immediately follow it up with why that advantage exists in the context of the question. You also need to decode the command words. If a question says evaluate, you can't just describe. You need pros, cons, and a conclusion. Before we continue, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Okay, moving right along to Section 2, thinking like an examiner. It's time to secure those top marks by stepping directly into the shoes of the person grading your paper.
Here's a crucial realization directly from the Cambridge Examiner reports. Generic responses rarely gain full marks. Specificity is your ultimate key to high performance.
If you write an answer that could apply to literally any computer system in the world, the examiner cannot award you top marks. We saw those red pen marks on Alex and Sam's papers. But if we transform those using our peel strategy, the red marks turn to green check marks. You don't just say file size increases. You say the image file size increases, which consumes more bandwidth when transmitting the image data from the robot to the central server. That is specific. That is examiner ready.
So what does the examiner actually want? We've distilled this into a computer science success blueprint. The core expectations for a top-tier answer require you to move way beyond basic theory into applied reasoning. First, use precise terminology. Do not say, the picture looks better. Say, the image has a higher pixel density, allowing for finer detail representation. Second, explain processes in a clear, logical sequence that another programmer could follow. Third, compare alternatives when necessary. And above all, strictly adhere to the given context.
Let me say that again, because it is literally the most important thing you'll hear today. Context is king. Is the scenario a school, an office, a robot's camera, an embedded system in a washing machine? If the question asks about a washing machine, do not start talking about 4K smartphone screens. Students often know the theory perfectly but throw away easy marks because they fail to anchor their explanation to the specific details provided in the prompt. Stay inside the context always. Now we're at Section 3, the 3-pass revision. This is a concrete 3-step implementation strategy to conquer this topic well before you step into the exam hall. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, let's get into our interactive workshop. This layered 3-pass revision style is incredibly useful because exam questions frequently combine theory with applied reasoning. Pass 1 secures your foundational definitions. Pass 2 is active practice, rehearsing worked explanations. But Pass 3, that's where the magic happens. This is where you adapt to changing scenarios. Let's do Challenge 1 right now, the data scan. Imagine a complex data table on screen showing a 1080p image with a 24-bit color depth. I'm putting a 60-second visual countdown timer in your mind. If you double the color depth, what happens to the file size? Quick. If you said it doubles, you're absolutely right. But the Pass 3 skill is justifying why it matters. If this is a live video feed, doubling the file size might cause buffering if the bandwidth isn't sufficient. That's the level of reasoning you need.
During that first pass of revision, distinguishing between nearby concepts is absolutely essential. The theoretical foundations often depend on separating things like memory from storage, or a compiler from an interpreter. Confusing these similar-sounding concepts is a frequent source of lost marks. Let's do Challenge 2, Find the Flaw. Listen to this flawed sample paragraph. To process the high-resolution image faster, the computer needs a larger hard drive to store the active image data. Did you spot the flaw? A larger hard drive is storage, not memory. To process an image faster, you need more RAM, memory, to hold the active data, not storage. If you write hard drive instead of RAM, you lose the mark. Train yourself on these specific comparisons.
Section 4. 4 prompts to success. We are going to unveil a core memory structure that guarantees you can formulate a complete analytical answer every single time.
This is the framework that prevents you from just dumping everything you know onto the page without direction. Ask yourself these 4 essential questions. 1. What is it? 2. How does it work? 3. Where is it used? And 4. Why is it better or worse than an alternative in that specific situation? Let's do Challenge 3, Speed Writing. I want you to imagine a 30-second timer on the screen. Try to write one perfect peel paragraph in your head about lowering image resolution for a web page. Go. You'd say, lowering resolution means fewer pixels. This works by reducing the amount of binary data required to represent the image. It's used on web pages to ensure fast loading times. It's better than high resolution here because user experience relies on quick page loads overriding the need for perfect image clarity. Boom. Full marks.
Let's look closely at how this builds by applying it directly to image resolution and color depth on this table. For what is it, you secure the key concept, like defining color depth as bits per pixel. For how does it work, you explain the clear sequence or the binary manipulation involved. For example, calculating file size by multiplying resolution by color depth. Where is it used? Anchors your answer directly to the scenario, maybe a smartphone screen, a website, or a robotics factory. Finally, why choose it evaluates the consequences. Does a 32-bit color depth provide a more realistic image for a photographer? Yes. Does it completely ruin the transmission speed for a basic security camera? Also yes. You have to evaluate the trade-offs.
And remember, real-world transfer matters massively. The technical patterns you learn for image resolution apply across entirely different technologies. The logic you use to explain why a high-resolution image slows down a school's local network is the exact same logic you use to explain why it slows down a secure banking communication or a retail point-of-sale system. Recognizing these transferable patterns helps you remember not just the technical name of the concept, but the actual logical reason for using it across completely different digital landscapes.
We've made it to Section 5, your pre-exam checklist. This is the final payoff, the ultimate system and mental checklist you should tick off while sitting right there at your exam desk.
Our final system relies on 3 rules: command word decoding, Peel framework application, and a time management matrix. Before you write a single word, you have to diagnose the demand. Ask yourself, what exactly is the task testing? Is the command word asking for a process explanation, a justification of hardware selection, or is it testing your logical reasoning? Are you spending 10 minutes on a 2-mark question, ruining your time management matrix? Once you decode the command word and diagnose the demand correctly, you completely eliminate the risk of writing a brilliant, accurate answer to the totally wrong question.
Here is your ultimate examiner-style checklist before you move on to the next question. Run through this list. Have you stated the key concept using precise terminology? Yes. Have you justified its use within the specific realistic scenario provided? Yes. Have you compared it with a related concept if necessary? Yes. And critically, have you double-checked that you avoided any vague, unsupported advantages like it is faster or it is better? Yes. This checklist ensures every single response you write is contextualized, specific, and totally examiner-ready.
I want to leave you with this powerful thought from our source material. If a learner can answer those 4 prompts aloud, the topic is usually ready for examination use. So challenge yourself right now. If I handed you a blank piece of paper and asked you to justify the exact color depth needed for a satellite imagery system, could you answer those 4 prompts out loud? If not, you know exactly what to revise next. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.